Hello. So now we will apply some of the concepts we learned about information visualization. And we're going to learn about a Python package called Seaborn. There are many packages in Python for visualization. Seaborn is unique in that it enables the visualization of statistical relationships and more generally creating visualizations for the purpose of statistical analysis. This makes Seaborn the go-to package for exploratory data analysis, especially when coupled with packages like stat models for creating regression models. So today we're going to learn about visualizing statistical relationships and visualizing distribution of data. A statistical relationship is a relationship between two variables. Seaborn offers a couple of functions for creating this visualization. There is one main function called REL plot for relation plot. And the relation plot offers different types. The two main types are scatter plot and line plot. We can create these types either by calling relation plot and passing a parameter kind, or using the special functions scatter plot or line plot. So let's take a look at some of the examples now. So we need to import the package Seaborn, and we usually give it the alias SNS. We'll also import the PLT object from matplotlib. Matplotlib is the package that Seaborn relies on. So matplotlib is a more general purpose visualization package. Beyond these importations, we're going to set the theme of Seaborn. This is not really necessary. We're going to go with the default theme if we don't set it. And then we're going to use matplotlib inline to make sure that the visualizations show in the notebook, inside the notebook. So let's take a look at one of the built-in dataset tips. So Seaborn comes with several built-in datasets for the purpose of exploring visualization options. So these datasets come with a package. We don't need to load any external files. Let's load the tips dataset. And let's, before looking at the visualization, look at the dataset really quickly. This dataset is about people tipping in restaurants. So we've got variables including the total bill, the amount of the tip, the sex of the person who made the tip, the client, whether the person was smoker or not, the day of that meal, the visit, the time, and also the size of the party. So this dataset allows us to explore interesting relationship across these variables. The main important one is what determines the amount of tip that people give in restaurants. This is an example of a relationship between two variables. A relation plot allows us to explore this relationship visually. And the basic kind of this plot is a scatter plot. So the syntax for relation plot is relation plot, the function, and then we need to specify the two variables on the x and the y axis. And then we need to specify the data set those two variables come from. In our case, x is total bill and y is tip, and data is tips. So if we look at this relationship, we can see that there is kind of a linear relationship between total bill and tip. The more the bill is, the more the tip is, and this increase looks like it's kind of a linear fashion, although there is more spread with larger bills than smaller ones. Alright, so let's take a look at fine-tuning this visualization. Now here we would like to add another variable into consideration, which is whether the person is a smoker or not. Remember from our discussion of the concepts, we can add more information by leveraging more channels in the graph. One channel that we have access to is color, and to map it to a variable we can use the parameter hue and map it to another variable, which is smoker in this case. And now if we create the visualization, we can see that the dots show in a blue and orange depending on whether the person was smoker or not. So if you look at this relationship, you can see for smokers, they're almost identical to non-smoker for small bills, but when it comes to small bills, it looks like smokers tip less than non-smokers, except we've got some outliers still. Now, many often when we have colors on our visualization, the colors may not be easily identifiable, especially if the visualization is printed out, for example, in black and white, or visualized in a screen of low color resolution, for example, on an e-reader. That's also the case if the person who's looking at the visualization has some issues interpreting and understanding colors, such as color blindness. So many often it's useful to add another channel to distinguish in between the two categories here, smoker and non-smoker. So what we've done here, we leverage another channel, which is style. So we get the tick here, the mark, is either a cross or a circle. So here we doubled down on smoker. We could have done only style smoker, and hence we get either a cross or a point. But we doubled down and we made this both the color and the style map to smoker. We obviously can leverage this channel for another variable. So for example, we can map it to sex in this case, and now we've got interesting differences between smoker and non-smoker in color, and between male and female in point and in tick. I think this is a bit too much, and now it becomes a bit hard to figure out these different 4 categories. But this is an example of leveraging visualization channels and mapping them to different variables from the data. Here is a similar example where we use style to map it to time. So we see differences between lunch and dinner, as well as differences between smokers and non-smokers. Another channel that we can leverage is the size of the marker on the visualization. So for example, we can say here I want to map size to size, and you can see that the size of the dot is now proportional to the variable size. It can be also made proportional to another variable, which is party in this case. So let's take a look at the data here again. It's actually size, not party, right? So the variable size. What I meant here is that it can be made proportional to another variable, and we don't have any quantitative variable beside total bill and tip and size. So now those different markers of different sizes are still close to each other. So you can see the difference here on the scale, but you can make it more kind of apparent by tuning in the starting point and kind of the minimum and the maximum size of these circles. By doing so, you add more contrast to smaller parties and larger parties in the data. Now let me go back to these examples here. In those 2 examples, I'm mapping size to hue. Now in contrast to smoker, where we had only yes or no, we map a quantitative variable that has more than 2 categories or values. You get kind of a shades of one color to distinguish between low values and large values. In this case, we got like light pink to dark violet in this case. So that's useful because size is theoretically unbounded. You can have very, very large parties. So the shades from light to dark will indicate kind of the magnitude of this variable here. And we can change the palette. For example, here we change the palette to make it a bit more greenish. So far we've been looking at scatter plots, and scatter plots are the default way of creating a relationship between 2 variables. Now, if this relationship is continuous, it makes sense to connect the dots and create a line plot. So for example, let's take a look at this example dataset. In this dataset, we're basically just simulating data with 2 variables, time and value. Time is just goes from 0 to 500 or 400 in this case, and value is a random number. But we're also looking at the cumulative sum of value. So this kind of looks like a time series, and if we visualize this relationship, we're going to get kind of a line plot. For each value of time, we're going to get the corresponding y value. The crucial point in here is that kind is line. If we delete kind, or if we set kind to be scatter in relation plot, we've got a bunch of points, right? But to connect the dots here, I can go ahead and tell Seaborn that, hey, I want to look this as scatter plot. Sorry, as a line plot. Now, if you're wondering why we're getting different lines, it's simply because we're just creating these numbers randomly. So each time I'm running this code, I'm getting a different set of these numbers. Now, the point of this exercise is to realize that the syntax is the same. The syntax is basically the same as with a scatter plot, and the only difference is that kind is set to line. So this directive here, g.autoformatxdate, is just a directive to format the x-axis properly. And in this case, we don't have issues because it's not really clutter. If it's cluttered, tilting them just a bit will help with the clutter on the x-axis. Now, by default, line plot will assume that the data is sorted. In this case, the data is sorted across the x-axis, which is time, because we've got this data here in order. If your data is not ordered, then in this case, Seaborn is going to still to order it. However, you can turn this kind of behavior and you can turn it off, and if that's the case, then the order will be the same order in the data set. And in this case, the line is not guaranteed, obviously, to be kind of a line because you're just jumping in between points. So let's do scatter here to show you the, oops, we can't do kind with a scatter, right? So we just have a bunch of random points here in space. In this case, we have random x and y, and if you're connecting them based on the x's without sorting them, you're going to get a zigzaggy line, as we can see here. In most of our applications, we're not interested in creating such a plot, but this is interesting for applications like random walks, where you want, for example, to visualize movement in space rather than a time series plot. All right, so many often we have multiple values of one variable for each value of one variable. Let's take a look at this data set, which is the Fmri data set. This data set has values for subject measured at different points in time. So we're measuring different aspects using the MRI machine. And those measurements are across region, and there is a value of a signal. Now, if we visualize here the relationship between a time point and the signal, we will come to realize that for each time point we get multiple observations because we have multiple subjects. Now, if this has been a scatter plot rather than a line plot, you can see that for each one of those time points you actually get a bunch of measurements, and the wider the measurements are, the kind of larger the error or the variance across these measurements. Now, switching to line plot, Seaborn will automatically summarize this variance by calculating, in this case, a confidence interval. So it's going to visualize the average and provide a confidence interval of 95% around it. So that already makes it pretty useful because you can see the trend and you can also see the variance across or over that trend. You can turn off this default behavior, but many often you're not guaranteed to get a really useful graph because it will be really zigzagging in between those values. So it will connect all of the dots here and then goes to the first dot here, connects all the dots here, 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 here. So you get this zigzaggy line, which is less useful or meaningful than the previous visualization. Now, similarly to what we've done with scatterplot, we can map color, for example, to another variable such as events, and we get two lines here, a line for each event, such as Tim and Q in this case. We can also add another channel, the style. So in this case, hue is mapped to region, and then the style is mapped to event. So you can see that we leverage color and also the style of the line to map two more variables into our data. We also have many options To know more about the options that relation plot or any functions offers, we can look up the documentation. To do it from the notebook is pretty easy if you position your cursor over or just after the parentheses and hit Shift Tab. You get contextual documentation that you can expand here, and here you're going to see all of the options and parameters that this function takes. In this case, I turned the dashes to false and the markers to true, so I see a marker point across each one of these points. So instead of seeing dashes in the style of the line, I'm visualizing this using the markers, the X's and the points. Very similar to what we've seen above. Usually it's beneficial to double down on a certain variable of interest, especially if you have channels at your disposal. So if you take a look at this figure, and again, same problem, if this figure is to be printed out, the differences between the blue and the orange may not be very apparent. So what we've done, we mapped event to both hue and style. So the difference between stem and Q is now emphasized both in color and also in style. This is an interesting case of not aggregating the data. And here, if we don't aggregate the data because the relationship between time point and signal, remember that by default Seaborn is going to average these different values of the same measurement on the line for the X. So if you go back to the original situation here, we get averages. Now we can turn averages off by setting estimator to none. If we set estimator to none, we get this zigzaggy line because all of the points here are kind of connected together. Now instead, you can tell Seaborn that I don't want you to settle for one line or two lines in this case because we have hue, but rather for each subject, which is another variable in our data, I want to see another line. Depending on how many values of that variables you have, your figure can be either meaningful or too busy. In this case, the figure is not that bad. Actually, it shows the variance across the subjects in our data. So all of these lines here represent measurements across different subjects, and that's also over 2 regions. So we get a bundle of these lines here. Here's another example from another data set. So let's take a look at this data set. This data set is called dots. This data set is the result of a biological experiment where the interesting variable is the firing rate of neurons in the brain. We have more variables here of interest that very often we would like to look at the relationship with firing rate. In this case, we can look at time and its relationship with firing rate, and here we map the hue and the hue to coherence and the style to choice. So we've got different lines for each one of these combinations between different values of coherence and different value of choice. The problem here is that hue is not the best choice for coherence. And that's because the difference in the values of coherence is not that large. So instead, we can specify a different palette to emphasize the difference across these values. So here we specifically created a palette in which the colors are really more different, and we passed it here instead of the default one to get more contrast. There are more options here, as we can see, and I'm going to skip those more advanced applications. As you see, the basic idea here is that once we figure out the visualization that we want to use, we can fine-tune it by leveraging more options.